Hey guys, what's up? Felix here. So for my project, I'm explaining how shells as a volumes of revolution works and why we use shells specifically over the normal washers and disk method and how it visually finds that volume. So why do we use shells? It's a specific type of scenario. When we're using washers and disks, we're doing so because we're spinning our area around an axis that is parallel to the axis that our function is in terms of. So since our function normally is an f of x function, it's in terms of x's, we're usually spinning our area around an axis that is parallel to the x-axis. It could be the x-axis, it could be y equals 3, it could be y equals 5. Pretty much our function, if it's a y equals function, we're spinning it around a y equals axis. But if we're not, let's say we're spinning y equals function around the y-axis, which is an x equals 0, then we can't use those washers, we can't use those disks. Instead, what we use is shells. So I'm going to explain to you how shells work, how they work visually, and why the math checks out. So here's a function, y equals negative 1/2 x squared plus 10. And we're spinning that around the y-axis from x equals 0 to the x-intercept. And so, similar to a Riemann sum, I'm going to do a very crude, rough approximation of how shells work that would yield a very terrible volume, and then show how we can use the powers of being able to make dx infinitely small to have the exact volume. So, similar to a Riemann sum, we have it kind of divided into these sections. There's 4 lines, the f of x of 1, f of x of 2, f of x of 3, and f of x of 4. And what we're doing with each of these lines is we're taking it and we're spinning it out towards us, then back to the page, and then back in. So for the first one, we're always staying 1 unit away from the y-axis in 3D. So this is like the label on a soup can, and we end up with this cylinder. And it's that line spun out around the y-axis. And then we go on to the next one. This f of x yields a smaller number, so it's a cylinder that's smaller in height, but it's wider. And then a wider cylinder, shorter cylinder, and then the tiniest cylinder, but the widest of them all. And so when we put all those disks together, we get that same roughly parabolic shape, just like a Riemann sum. It's just an approximation, but it's spun out, and we have that 3D version. And so each of those corresponds to one of the altitudes on the function that's been spun, just like the label on a can. I mean, these are obviously all varying in height and in width, but they're that same idea, that it's just a rectangle, like end to end, that approximates the function. And so let's say we take one of these soup can labels, and if we cut it, we would be able to unroll it, and it would just yield a rectangle. And rectangles are the easiest thing to find in area. We just multiply the height, and we multiply the base, the length. So what is the height for this? Well, the height is just whatever the f of x is at that point, whatever the function, what you solve for when you plug in that x. And the width is the circumference with a radius of that x. So if you're at x equals 3, you just take that, double it to be 6, and then multiply that by pi. So that's the actual circumference of this, and that's your width of your rectangle. And so if you multiply those two numbers, the width and the height, you would get the area of this. And then if we do an infinite summation where these get closer and closer together, then we can approximate, and then once we have it at infinity, we can directly solve for the volume of that solid shape. Mathematically, the way we represent this is the volume is that integral, that summation of the circumference, which is the base, times the height. And we know the circumference is 2 pi r, and we know the radius at that point is just the x value, because right now we're spinning it around x equals 0, or like the y axis itself, x equals 0. So we don't have to worry about the axis for now. And we know that the height of each of those little cylinders is just the function of that x. So we end up getting a volume that is 2 pi x times f of x dx, and then since 2 pi is just the constant, we can bring that up front. And we end with our x, f of x. And so for f of x, we just plug in our original function, which was negative 1/2 x squared plus 10, and we can just take that integral to find the volume along those, from a to b along that domain. If we don't end up spinning it around the y-axis, if we actually do have a value, we just have a, that constant there, the lowercase a as the axis of rotation. For example, x equals 4 or x equals negative 12. We just set that in there, and we're just always subtracting it to find what like the distance from that axis is. And then other than that, our math is completely the same. And we can find a volume spinning it around even an axis that's far away. We'll just have like a hole, or like a donut, for example, has that big hole in the center, and we're spinning it around an axis that is like where there isn't any like function there necessarily, but we're spinning it around that to make that hole in the center.